Hey everyone! In this Technology Insight episode, we're going to look at an interesting development for incident and flow monitoring detection on motorways using fibre optic cables to provide linear detection along the entire length of the road rather than at individual points along its length. Anyway, I'm Alistair and this is at ITS Now. Traditionally, incident and flow detection on motorways and freeways used inductive loop detection as sensors to capture real-time traffic data. This includes not only vehicle speeds, but also other characteristics, such as headway, which is the distance between vehicles in a lane-by-lane basis. This information is then used to automatically set warning signs or to reduce speed limits and can warn operators in the event of an incident occurring. Although inductive loops are still seen as the gold standard against which other emerging technologies' performance are measured against, there are a number of issues with these that are widely recognized, including in this type of application only being located every 500 meters or so along the highway and being very intrusive to reinstall, for example, when the road is resurfaced. I'll include a link to our episode about inductive loops if you're interested to see more about these. Over the years, a number of other technologies have been used in an attempt to overcome some of the issues associated with inductive loops. Most of these have used overhead or verge-mounted radar or optical detection technologies. Although these can provide a very high level of performance when replacing a location-based inductive loop incident detector, their ability to provide coverage for a length of highway, such as for stopped vehicle detection, where the accuracy tends to degrade further away from the sensor you get. Although technologies now tend to include capabilities to track individual vehicles, their ability to achieve this can be compromised. For example, because of obscuration issues from passing trucks blocking the view of vehicles in other lanes, and also by poor climatic conditions, such as heavy rain or snow, particularly at the outer reaches from a detector, say 200 to 300 meters away.
Remember to hit subscribe for ITS Now.
To overcome these restrictions, an alternative in-ground technology has been used which provides a continuous linear detection capability. Distributed fibre optic sensing, or DFOS for short, uses a fibre optic cable laid in a buried duct next to the road. This technology was originally used in security applications to monitor assets such as oil pipelines or security fences around military sites or other sensitive locations such as airports or borders. By sending pulses of light down the optic fibre, it is possible to sense vibrations caused, for example, people trying to climb over, cut through or dig under a fence. This is achieved by monitoring the backscatter of signals reflected back to the source. In highway applications, this ability to sense along the entire length of a fibre optic cable opens some really interesting possibilities, particularly for motorway incident and traffic flow applications where you want to monitor hundreds of miles of road. And the analysis is carried out using an optical integrator, which is a device attached to the end of the fibre optic cable. This uses AI to analyse the data in real time. The vibrations caused by the tyres of passing vehicles can be used to reveal how many vehicles are on the road and how fast they're travelling. The Japanese company NEC have developed this technology to extract further insights of vehicle behaviour such as detecting irregular lane changes by vehicles travelling in the same direction, enabling it to detect abnormalities on the road, which could include incidents or road defects. Previous implementations of DFOS applications have only been able to detect linear traffic movements, so could see where the bunching of vehicles forming congestion in sections of motorway, but now, by determining where the centroid of individual vehicle vibrations is emanating from, can identify when vehicles change lanes. This is achieved by tracking individual vehicle movements to determine abnormal vehicle behaviour. Vehicle vibration frequency is higher for vehicles travelling on lanes closest to the installed fibre-optic cable. So this difference in frequency characteristics for near lane and far lane vehicles can then be used to detect lane change behaviour. From my own experience of deploying this type of technology, it tends to work best when the fibre-optic cable is located in a fairly shallow duct on both sides of the motorway. Although the system can differentiate between traffic moving in both directions, the effectiveness during congestion events particularly appears to be better than trying to use a single fibre on one side of the motorway. I designed a project where I included a duct in the central reservation concrete barrier for this application, but I haven't seen any results to assess how well this worked, so maybe something to consider. The obvious benefit of equipment topography used with DFOS is the ability to monitor entire lengths of highway, but with minimal equipment located along the road. A single cabinet can be used to monitor miles and miles of highway with just a fibre-optic cable located along the side of the carriageway. So a huge reduction in roadside equipment to install and maintain, therefore providing both financial benefits and reducing the exposure of maintenance staff to hazards associated with working on the roadside. So in this episode, we've seen how DFOS technology has been developed to provide more insight of traffic flow on our busy roads, whilst offering the opportunity to simplify the detection infrastructure deployed on our roadsides. Thank you to NEC for taking part in this episode. Find links to them below. Right, lastly, could I please ask you to subscribe to our channel? It really does help us to bring you further videos about ITS. Thank you again to everyone who has subscribed. Thanks for watching. See you next time.